37 minutes. What's up, Wes?
Nothing really. How about you?
Just excited that today's the last day.
It is pretty exciting.
Yep. All right, here we go. Questions on the homework?
Nothing in particular.
Okay. Let's see. Number 1 was 1/5. Number 2 was 5. Number 3 was a over 2. Number 4 was 3. Number 5 was 1/3. Number 6 was c over 2b. Number 7 was negative 4y squared. Number 8 was negative 3r squared over 2. Number 9 was ab over 2c. And then we came to the ones you had to factor. So 10 through 16, you had to factor each one of these. All right, number 10, it factored to a plus 2, the whole thing, simplified, a plus 2. Number 11, after everything was factored and canceled, was 3x minus 2y. Number 12 was 3a minus 2. Number 13 was 1/3. And then it start getting complicated here. Number 14 was c minus d all over c plus d. 15 and 16, you had to factor each quadratic. 15, it finally reduced to t plus 1, just plain old t plus 1. And on number 16, it was 5 over a minus b. Wes, did you try number 18?
No, I did not.
Okay. All right, any other questions? All right. Hey, last section, and then we go on Thanksgiving break. So, and we will do a review. The review will probably not just be reteaching 7.1. I'll probably review some other stuff. But I will reintroduce you back to 7.1 when we get back. All right, here is the homework for today. First homework of chapter 7. Chapter 7. We are past, let's see, is there 14 or 13? I always forget. 14 or 13 chapters. It's 14 chapters. So this would be the midway point of the book, chapter 7. Right on time. We'll finish this. Then we'll study for our semester final, take our semester final the last 3 days of the quarter. They will be half-day schedules. Wednesday, Thursday, Friday. You'll take 2 tests a day. So you come in, probably take a test for about an hour, hour and a half-ish. Go to student advisement, spend about 45 minutes there studying for your second test. Take your second test, go home. All right, so chapter 7, it is a very challenging chapter, but the nice thing is that today is a pretty easy day. We're going to start off with something called ratios and proportions. The entire chapter deals with something called similarities, but we'll start off with ratios and proportions. So generally speaking, get it? Generally speaking, the chapter is very challenging, but today's pretty easy. It's a pretty easy day if you pay attention. So here we go. First definition, write this down, please. Now you've dealt with ratios for many years. A ratio is a comparison of 2 numbers using division. That means it's a fraction. So 2 numbers compared using division, that's called a fraction. And it is usually expressed in simplest forms. Now, if we're doing operations or fractions, we always reduce the fraction. But if we're talking about a ratio, it is generally your choice of whether you reduce the ratio or not. Here's an example. The ratio of 8 to 12. So we need to compare these two numbers using division. We always write them in the order that they appear. So 8 would be the numerator, 12 would be the denominator, and there you go. There's the ratio of 8 to 12. Now you can reduce this, right, to 2/3, and 8 over 12 is the same ratio as 2 over 3. If you remember way back the last time that you had a class on ratios, there's a second form to write ratios, and it's called colon form. Colon form is literally you take the two numbers, you stick a colon between them, and you're done. There's also the word form, and that's just what you see here in red, the ratio of 8 to 2, T-O, not T-W-O, 8 to 2. And this is called word form, this is called fraction form, and this is called colon form. So there's really three ways of writing ratios, and this should not be new to you. You should have seen this, and it should be familiar with you. All right, we good?
Yeah.
All right. So obviously that's in algebra or pre-algebra. So how do you do ratios in geometry? Well, it's pretty simple. They'll give you some geometric shape. Looks like we have a trapezoid here, although it doesn't say it's trapezoid. And you'll have a couple questions. It says, what is the ratio of side OI to side ZD? And no, we're not going to overthink this. We're just going to make the ratio. Side OI has a length of 14. Side ZD has a length of CB, and you just set up your fraction, right? We could reduce that if we wanted to, divide top and bottom by 2, and we would get 7 over 3b. So it's up to you whether you reduce it or not. It's not a requirement, but generally speaking, we will always reduce our ratios. We can do the same thing with angles. So it says, what is the ratio of the smallest to the largest angle? We have a problem right here is that this angle is not listed. Well, if we remember right, all quadrilaterals, there's 360 degrees on their interior angles. See, 60 plus 70 is 130, 130 and 120 is 250, and 360 minus 250 is 110. So this angle, the unknown angle here is 110. Well, it did say smallest to largest. That was a whole lot of work for nothing, apparently. So let's see, the smallest angle would be 60. The largest angle would be 120. So if we write that as a ratio, that would be angle D over angle Z. In other words, 60 over 20, or 1/2. Okay, so ratios in geometry, we got them. They're pretty easy to do. Not much going on there. You won't have any issues making ratios. Tonight they'll have you make a couple ratios. All right, here's where they're going to throw a curveball at you. So notice it's just text here. They're certainly talking about geometric dimensions here. I'm talking about length and width of a poster, so basically probably a rectangle. So it says a poster is 1 meter long and 25 or 52 centimeters wide. Find the ratio of width to length. And we got a problem here, right? The problem is that we have differing dimensions. One is in meters and one is in centimeters. Just remember, when you do a ratio, if you're dealing with the same type of measurements, in other words, you're dealing with either distance or liquid volume or area or whatever, the units must be the same. So in our case, we got a problem because this one's in meters, this is in centimeters. Another example would be if this was in yards and this was in feet, we need to convert both of them. If the ratio is something like miles per gallon, well, you can't convert miles to gallons or gallons to miles. But when you have similar units, distance, you got to convert them. So I don't know how well you remember metric conversions, Wes. Do you remember anything about metric conversion?
I don't know how to explain it, but it should be either 100, right? 100
Well, let's see. So just remember, ratios must be in the same units. So we'll review this real quick. Quick metric review. These are not all the metric units. These are some of the most commonly used metric units. And they go by this acronym right here. Do you remember what K stands for?
Kilo or kilo, right?
Yep. And that means what mathematically?
1,000.
Yep.
Right.
B stands for your base units. That's your meters, liters, or grams, abbreviated M, L, or G. K does in fact stand for 1,000 kilo, and the abbreviation is K. We rarely see the H. I'll show you one example today, and you'll probably never see it again. You remember what H stands for?
No.
Yeah, no one does. Well, it really means 100, and it's hecto, and the abbreviation is an H. We get these two D's, everybody messes them up, so I always just tell you, hey, put them in alphabetical order. One is deci and one is deca. So if you put those in alphabetical order, deca comes before deci. A comes before an I. The abbreviation for deca is DA. It's one of the only ones that has two letters on it. The base unit, right, that would be a 1, and that's ml or g, depending upon whether you're dealing with meters, liters, or grams. This D right here, we'll see it a lot, and it stands for deci, just the D. The C stands for centi. It's the other one that has, it stands for 100th. And the last one, the M, which is easily confused with meters. It's not meters, it's milli. Milli means 1,000th, sorry. And its abbreviation is M, right? There's a problem that both this and this use the letter M. Just so you know, if milli is involved, there's going to be two letters, millimeters, MM, milliliters, ML, milligrams, MG. If it's just meters, there's just going to be one M all by itself. All right. Do you remember the saying, Wes, for these letters right here?
I do not.
King Henry died by drinking chocolate milk. King Henry died by drinking chocolate milk. King Henry died by drinking chocolate milk. And believe it or not, this saying right here allows us to do our metric conversions really easy. But you do have to remember King Henry died by drinking chocolate milk. And further, you got to remember that the B stands for meters, liters, and grams. So let me show you how this works. If I want to convert 3.5 meters to centimeters, we follow it in the order what it says, meters to centimeters. Step number 1 is we find out where meters is. Now you really want to say it's right here, but it's actually the B. The B is your starting point. I'm starting with meters. I'm going to centimeters, so I'm going to the right 1, 2 letters, 1, 2. So if I go from the B, that's the meters. Why is it B? It stands for meters because the B is base. It stands for meters, liters, and grams. I go from the B to the C, I'm going 2 letters to the right. Why is that helpful? Because that tells you how to move your decimal place. So to convert 3.5 meters, here's 3.5 meters. I added some zeros. I just go 2 decimal places to the right, 1, 2. So in other words, 1, 2, 350. So there are 350 centimeters in 3.5 meters. This is why everyone likes the metric system, because as long as you can remember King Henry died by drinking chocolate milk, it's really easy. If I ask you to convert yards to miles, well, you got to remember how many yards there are in a mile. No one remembers that except for math teachers. But everyone can remember King Henry died by drinking chocolate milk. One more, 27 deciliters, 27 deciliters to hectoliters. Deci, that's the hard one. You got to remember alphabetical order. Deca, deci. So we're starting right here, deci, and we're going to the H. So we're going 1, 2, 3 decimal places to the left. So we take this 27, and I need to move the decimal place. I already added some zeros here. 3 decimal places to the left. 1, 2, 3. So right here, so I get 0.027 deciliters. Wes, have you ever done this before?
Yeah, a lot actually.
Okay, so this is how how it's done, and as long as you can remember King Henry died by drinking chocolate milk, you'll never have a problem converting metric. Now, I just want to point out there's more of these letters. Just these are the primary ones that we use. When you get to physics, you have nanometer, you have larger, as well on the other side. Pico, there's lots of them out there, but these are the ones that we use in math and generally speaking in physics. If you get really, really, really small or really, really, really large, that's usually above the level of high school level math and science. All right. One more time. Let's see. Kilometers to meters. Kilometers to meters. Well, there's no. The K is right here. Remember, although you really want to say this is meters, this M, the meters is actually underneath the B. for meters, liters, and grams. So I'm going from K to B. So K is my starting point. So if I were to do that, I would go 1, 2, 3 to the right. So if I take 4.3, I'll add a bunch of zeros. And then I move it 3 decimal places, 1, 2, 3. You can see that I get 4,300 meters. Second one there, if I go from 40 millimeters, here's the M, that's my starting point, to meters, meters is over here, I'm going 1, 2, 3 to the left. So I write 40, I'm going to put some zeros here so I can move my decimal place. My decimal starts here, I'm going 1, 2, 3 to the left, 1, 2, 3, I get 0.04. So 0.4 meters, 0.04 meters in 40 millimeters. And that's how it's done. Questions? There aren't too many questions tonight. This isn't what the homework is on mainly, but there's 1 or 2 questions where you have to, when they ask you to make a ratio, you have to convert. All right, so back to ratios. So here was our original problem. Poster is 1 meter long and 52 centimeters wide. Find the ratio of width to length. So let's see, the width would be this. That would be your numerator, and your denominator would be that. Okay, so width to length, we can either convert meters to centimeters or centimeters to meters, either once. There's 2 possible answers here. If I do meters to centimeters, King Henry died by drinking chocolate milk, it turns out that that would be 52 centimeters would convert to 0.52 meters. So that is going to be my width. That's going to be my numerator. We went width to length. So you get that. Now we have a problem here, and the problem is that we don't do fractions with decimals in there. So how do you change this? I don't know if you remember this. We're simply going to move it 2 decimal places to the right. That's the same as multiplying the top by 100, and whatever you do to the top, you do to the bottom. So if you move the top 2 decimal places, move the bottom 2 decimal places, and we get 52 over 100. Now that was converting centimeters to meters. We can equally convert meters, right, to centimeters, right? So if we convert, I'll just show you another possible answer here. Oh, by the way, we need to reduce that fraction. If we do centimeters to meters, right, that would be 1 meter would equal 100 centimeters. So if we were to write that fraction, now everything's in centimeters. So this would be 100, and this is already 52. So we get 50. Oh, wait, it's the same thing. So notice whether we converted from centimeters to meters or meters to centimeters, eventually we get back to the same ratio. A lot of people try to overthink this and say, well, which would be the one that wouldn't require me to have a decimal? Okay, if you can think that far ahead, good for you. The rest of us are just going to pick a method and go with it and just deal with either the decimals or the non-decimals. Does that make sense, Wes?
Yes, a lot.
All right. So that's that's stuff that technically you should have walked into my class already being able to do. Here comes the new stuff. All right. This is pretty easy. It's also pretty slick. All right, we got a bag of marbles. Wait, I thought this was geometry. We got a bag of marbles containing red, blue, and green marbles. So inside this bag, we got an unknown number of marbles, but we do know that all the marbles are either red, blue, or green. There are twice as many blue as red. There's 4 times as many green as there are red marbles. All right, so the questions will ask you to state something in ratio form about the relationship between the colors. Here's 3 different questions here. I want you to compare red to blue. So Wes, what would be the fraction of comparing red to blue?
1/2 of 1, red being 1 and blue being 2. Or...
Okay, I'm going to write mine in colon form. All right, so 1 to 2. There, for every 1 red marble, there's 2 blue marbles. How about red to green?
It'd be 1 to 4.
Okay, and here's the issue, is that I'm asking you to do blue to green. It never says anything about blue to green. However, what you can do is you can look at these 2, right? And these 2 will tell you. Comparing red, that means for every 1 red marble, there's 2 blue. For every 1 red marble, there's 4 green. So we can compare if we look at that information, because that information would be the blue to the green. So what's the ratio of blue to green?
2 to 4.
Yeah, that's where that comes from. Okay. Further, right, we can write the relationship of all three colors to each other if we just write it, and you've never seen this before. We're going to write a triple colon form ratio. That sounds a lot of words there. All it means is compare red to blue to green. So red to blue is 1 to 2. Green is 4. So if I want to do red to blue to green, take a guess at what the answer would be.
I have no idea.
Well, red was how many marbles?
1.
Right? Blue was how many marbles?
2.
And green was?
4.
That doesn't tell us how many marbles in the bag. It just simply tells us what's the ratio. I mean, there might be 10 red marbles in the bag, but if there's 10 red marbles in the bag, there's 20 blue and there's 40 green. That's the ratio. Here's a triple ratio. And by the way, it could be as many colons as you wanted to. And the reason why we choose to write this in colon form rather than fraction form, because that would look weird. 1 to 2 to 4 just doesn't look right. Right? It's also mathematically not correct either. So that's why as soon as we're comparing 3 or more things, we always use colon form. Okay. If it's just 2 things, sure, we can write it in fraction form: 1/2, 1/4, 2/4. Okay. All right. Have you ever heard the word pièce de résistance?
It sounds French, but no.
You know, a dessert with a cherry on the top?
Oh, it's that.
Yeah, so when we say the pièce de, it literally means piece of resistance. So the pièce de résistance means, and the most interesting part. So the most interesting part of what I just showed you is that we can do the following. All right, and it will be easy as well. It says the measures of, now we're in geometry. The measures of 3 angles in the triangle are in this ratio, 2 to 2 to 5. It says find the measurement of each angle. How in the world are we going to find angle measurements if they give us a ratio? Notice there's no angles here at all. It just says that they're in a ratio of 2 to 2 to 5. This sounds like it can't be done. This is pretty slick. And if this is the one thing you take away from the class, this is the most important thing, and it will be on the test. It's certainly on homework. All right, so you're going to be given a shape. You're going to be given the ratio of either the sides or the angles or both for that particular shape. So in this case, we have a triangle. There's 3 sides. And these are the ratio of those. In this case, it says angles. It's 2 to 2 to 5. So here's how it's done. We let X represent the measurement of one of the angles. It doesn't matter which one of the 3 angles in the triangle. What we know for any triangle is that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3, it's equal to 180 degrees. And it turns out if we combine this ratio with this statement, letting X represent one of these angles, we can find out what all of the angles are. Seems like not possible, but ends up being possible. So for instance, we will let measure of angle 1, which is this 2 right here, represent X, right? That means there's 2 of them. I don't know how many degrees X is, but if X represents the measurement of an angle, there's 2 of them. And then the second one, there's 2 of them. And the third one, there's 5 of them. If you think about that marble thing we just did. For every 2 marbles of this type, there's 2 marbles of this type, and there's 5 marbles of this type. So the only thing the difference is, instead of talking about marbles, we're talking about angles, angle measurements, I should say. So degrees. So here's the setup. They're going to give you a shape. They're going to give you a ratio. All you do is take the ratio and put an X on everything and let it equal, if we're talking about angle measurements, let it equal the sum of the angles of that particular shape. Since it's a triangle, it's 180 degrees. If it was a quadrilateral, it'd be 360 degrees. If it was a larger n-gon, then you would do n minus 2 times 180, figure out what all the degrees are, and go from there. I don't believe they give you anything larger than a triangle. I'm flipping my page to try to get to homework real quick. Let's see. No, it looks like triangles. Triangles. They got a hexagon as well too. So all the way up to a hexagon, it looks like, for homework. Okay. Now all we're going to do is solve this. 2x plus 2x plus 5x. That's what?
9x.
Therefore, x equals
180.
x equals
9.
x equals. One more try.
Wouldn't it be 90, right?
So if we divided both sides by 9, we would in fact get.
You would. I can't think right now. Sorry.
What's 18 divided by 9?
2. Sorry.
So 180 divided by 9 would be
20.
So what you just found out is you didn't find out a specific angle, you just found out what x represents. To find out what the angles represent, now we throw this 20 back into these values right here. So we said angle number 1 is going to be equal to 2 times x. Therefore, angle number 1 is equal to 2 times x. So x was 20. Therefore, angle 1 is
40
degrees, right?
Mm-hmm.
Therefore, angle 2 is also
40 degrees.
And angle 3, which was 5x, is equal to
100 degrees.
Boom. Check that out. You figured out what were the angle measurements of a triangle just from its ratio of its angle measurements. All right, that's pretty slick. So that's how it's done. The only difference between this and doing it for a hexagon is that for a hexagon, the angles would add up to, let's see, n minus 2. 6 minus 2 is 4. 4 times 180 is what? 720. Okay. All right. One more time. Let's see how this is done. So it's the same thing. We're trying to find 3 angle measurements of a triangle. The ratio is 5 to 7 to 8. So it's scalene, right? By the way, the previous one was what kind of triangle?
I can't name.
Well, the 2 angles are the same. That makes it.
I can't remember right now.
Isosceles.
Oh.
Yeah. All right. So this one is scalene because none of the angles are the same. All right, but the process is still the same. We let x equal one of the angles. We set each one equal to its ratio with an x attached to it, and we simply solve. Okay, 5x and 7x is
12
plus 8.
20.
Okay, therefore x equals.
Today is not my forte. I can't do it. It's in my head right now.
18 divided by 2.
9, it's 90.
All right, so 9, right? So 180 divided by 20 is 9. All right, now we take this value right here and we throw it back in for, this is angle 1, this is angle 2, this is angle 3. So we throw it into each angle and we simply do that math. So it looks like angle 1 is 45 degrees. Angle 2 is
60.
63.
Yeah, 63.
And the last one?
72.
All right. So you just figured out the 3 interior angles of a triangle based solely on the ratio of its angle measurements. Okay. That's a skill that you will have to use tonight for homework. All right. Just do a quick couple classroom exercises. Notice it says the first couple ones, all you're doing is reducing fractions. Hey, that's what we just did practice on for our algebra review, so they will ask you that. And then they will simply give you something like this, some geometric shape, and ask you to set up the ratio. So for instance, on number 8, they're asking you to look at this segment right here. What is the ratio of DI to IS?
Give me a second.
Don't overthink it. Just do exactly what it says right here. DI to IS.
Would it be 14?
Well, they're just literally asking to replace DI with its measurement. How long is DI?
10. Oh, I'm so confused.
So what's the ratio?
10 over 10, 14. 10
4. 14, 10 to 4.
Yeah.
Now you could reduce that to 5 over 2. How about ST to DI?
12 and 10.
12. DI is 10. 12 to 10.
Yeah.
Then they're going to get more complicated. And now you will have to actually do some math. How about IT to DT?
16 and 26.
All right, now you got it. And then you're not going to be hung up by the fact that they have a triple colon form 1 here. You would simply do that. All right, notice this question right here, number 14. This would be the one where you'd have to do your metric conversion, okay? And then that would be it. Notice right here, this would be like one of the examples we did previously. 1 to 2 to 5. There would be your initial setup right there, and they're just asking you, could the numbers be these? So let's see. 1 to 2 to 5 would be, you take the first one, you double it, and then you multiply it by 5. So if the first one is 5, if we double it, we would get, in fact, 10. And if we took the first one, which is 5, multiplied by 5, we don't get 20, we get 25. So that one's not possible, right? Oh, I'm sorry, it's 10 to 20 to 50. So, oops, I messed that one up. 10, 12, oh yeah, that one would be possible. How about 3, 6, 20? If 1 is 3, if you double 3, you do get 6, but 3 times 5 is 15. So this one will be a no. Okay, and then that one will be a yes. All right, any questions on anything we did today, Wes? Since you were the only one in class today.
No, I have no questions. I think I'm pretty good.
Cool. All right, well, you have a wonderful Thanksgiving break. I know I will. I hope to see you guys on Monday when we get back in school and we get back to normal school.
Yeah, have a good Thanksgiving.
You as well.